in preparation for 2 sample tests. Last time we talked about 1 sample test with the 1 sample t-test, and we talked about a Wilcoxon sign ranked test. And it is fair, sometimes you will want to analyze a single distribution relative to an expected mean or central tendency. But more often than not, when we think of science, one of the things we think about is making a comparison. We may want to compare an experimental treatment to a control treatment. We may want to compare one drug to a second drug. We may want to compare the effects of one habitat to another habitat, or a conservation treatment in one case to another case. We like to make comparisons, male versus female, Floridians versus Georgians. We like to make comparisons, and you wouldn't want to do that with a 1 sample test, because then you would only be looking at one of the populations. Instead, you want to have 2 samples. Yeah, I can find the screen. There it is. 2 sample tests. So, let me see if we can. Oh, wow, we flew. We went the wrong way, though. So down, down, down. Here we are. Okay, so to do that, the simplest way is something called a 2-sampled t-test. This is a parametric test that makes the same assumptions of our 1 sample test, and that is the data are normal and the data are independent. So we have our little bell curve, and the collection of one data point is independent of the collection of another data point. Similar to our other tests, what we are doing is we are comparing the central tendencies relative to the variation. So when we look at the equation for a t-test, we're calculating a t-statistic. As a reminder, we calculate the test stat relative to the degree of freedom. That gives us our p-value. In this case, we have the mean of our first sample minus the mean of our second sample. If x bar 1 is very tiny and x bar 2 is very large, that will make t large. If x bar 1 is very large and x bar 2 is very small, that will make t large. If they're about the same size, maybe they're both small, maybe they're both large, then that will make t small. So, similar to before, the larger the test statistic, the more likely we're going to get a small p-value, because it's unlikely to be random. But it's not just that we compare means. What we're doing is we're comparing those means relative to the variation. And this is the standard error of the mean for the first population plus the standard error for the mean of the second population. Now there's some goofy math going on. We have to take the squared terms, we add them together, and then we take the square roots. That's just some math that is embedded to creating the distribution necessary to calculate a p-value. Do you have to understand the logic of that? Sure, if you get off on calculus. If you don't get off on calculus, just notice that you're comparing the difference between the central tendencies relative to the variation. And if you do get off on the calculus of stats, there are a lot of good classes about that, but this is not one of them. We're interested in biology. So, in class, I'm not going to talk about that. I'm just going to ask you to write out the equation in words, which will reinforce what we just talked about on the video. So, the trouble is, a lot of times our data are not normal, and we may have a skewed distribution. We may have a uniform distribution. We may have a beta distribution. We may have even a binomial distribution can create some weird structure that doesn't fit normality. So when we do this, we have to deal with the data in a non-parametric fashion. For that, we could use something like a Mann-Whitney U-test. And this does some weird things. The first thing it does is it takes each and every one of your numbers and it ranks them. So if you're measuring height of individuals to the closest centimeter, instead of actually using 175 centimeters and 155 centimeters and 181 centimeters, what you do is you rank them all so that the smallest value gets the rank of 1, this next value gets the rank of 2, and then 3, and then 4, until you get to the highest value, which is your sample size, n. And what the Mann-Whitney U-test does is it compares the sum of the ranked values relative to the sample size. I'm just going to delay that. Whew, that's a beastly equation. but it's not. It's actually the same basic thing. What we do is we calculate a value of u. It doesn't matter which one you calculate, because these are proportional values. I'll describe that in a bit. But what you're doing is you're looking at the rank of the first population minus this standardizing factor. Well, in this case, it's not the variation, it's just sample size. So you sum of your ranks for first population minus basically a measure of how many data points you collected. The 1 and the 2 are just mathematical properties necessary to create that distribution so we can calculate a p-value. You could do this for U1, you could do it for U2, it doesn't really matter. Again, the sum of the ranks minus population size, sum of the ranks minus population size. The p-value sometimes is based on the larger of the two u values and sometimes based on the smaller of the two values. Again, this matters if you're using a table. It does not matter if we're using R because R will just do it for us. A little interesting property is that the two u values, when you add them together, they will equal the product of the sample sizes. So if you have 20 samples in the first population and 10 samples in the second population, then the product of those is 200. U1 and U2 will equal 200 when you add them together. So if U1 is 150, well then U2 has to be 50. If U1 is 190, then U2 has to be 10. If U1 is 101, then U2 has to be 99. They are proportional. So that extremely large values of U and extremely small values of U suggest a statistically different samples. If the U values are relatively the same, then it suggests that there's no difference between the two groups. So again, we're kind of working with that same structure. Even though the math looks different, it's the same basic property. We are able to compare our two populations. If they are dramatically different, then we have significance. If they are similar, then any difference is just random. And we control that relative to some standardizing factor. Many times it's variation, but when the rank test, it's sample size. So R1 minus N1 times N1 plus 1 divided by 2. Ooh, kind of ugly, but it works. So we have a problem. And the problem is sometimes what we want to do is we want to compare the same individual. So what do they look like before versus after a treatment? What happens when we collect consecutive measurements? What if we have paired measurements? Well, we can't use a t-test and we can't use a Mann-Whitney U-test. And the reason is we lose a tremendous amount of variation. In class, you will tell me what. Right now, I'm just going to tell you lose a ton of information. You could take the sign difference, but again, we're working with a lot of problems there because again, we lose a ton of information. One of the things that the sign difference expects, and the one sample t-test expects, is that the data are independent. But in this situation, the data are not independent. What you start off with and what you end with are related. So if you have a before test in a class and you rock it, when you take the after test for that exact same class, you are likely going to rock it. You're going to improve, but you're likely going to rock it. If you take the before test at the beginning of class and you do very poorly, and then you get all the information from the class and you take the after test, you are likely to improve. There's no question about it. But you're starting from a lower base and the degree of improvement is probably not going to be as dramatic. So what is interesting is we want to see how much change occurs within the individual, not as an average of the population. So, how do we deal with that? Well, one of the ways we can do it is a paired t-test. And we'll be talking about this in class, and we'll do some procedures with a paired t-test. It's the exact same command as a t-test. You just add in a function, comma, paired equals capital T for true. But if the data are non-parametric, we have another problem. What we do here is we do something called a Wilcoxon matched paired test. The math in these cases we're not going to talk about. Not that terribly important because really what they are is just another type of procedure that is similar to what we had with the t-test and the Mann-Whitney U-test. But we are going to run them in R so that we can see how we get different information based on that evaluation. The rest of this we'll talk about next time.